Good afternoon, everyone. Welcome to the seventh problem solving session of the structure analysis course, which is provided by NPTEL, wherein we will see the different problems related to the topic that we have covered in the week 7 of the structure analysis course. So, let me share my screen first. Okay. Yeah. So, I hope the screen is visible to all of you. Okay. So, let's get started. So, uh, my name is Pranav Mahajan. I am a research scholar in structure analysis engineering division of Department of Civil Engineering, IIT Madras. I am a PMRF scholar assigned as a teaching assistant for this NPTEL course, wherein we have solved various problems related to different frames, beams, how we have calculated the values of loads and deflection at various points of the section that we have covered till this 6 weeks. Let's first recap that. So, till now, what we have covered is we have completed the first half of the structure analysis course, wherein we have covered the whole analysis of the statically determinate structures in how we have started and till what point we have reached. Let's have a recap for that. So in week one, we started with the equilibrium equation. So we have three equilibrium equations. How to utilize that? You might have used these equation in strength of material also, and also in your higher secondary courses for mechanics. That how you utilize these equations to solve a problem related to the mechanics of a structure. Then we have also determined the stability of a structure based upon the determinacy of the structure that we have obtained, and we have also drawn the shear force and bending moment diagram at various sections. Suppose we are considering at section, so in which we need to determine what will be the value of shear force and bending moment at that particular point. So if we have drawn the shear force and bending moment diagram, we can easily interpret the value that is obtained at a particular distance x. Then we have moved to the second week, wherein we have seen the problem of a plane truss. We had considered that a truss to be a two force member, that is, it is capable of taking the compression as well as the tension forces along its axial length. So we have found out that to determine the forces in various members of the plane truss, how we have it done. So there are two methods. So first method is method of joints, and another is method of sections. So in method of joints, we have taken the equilibrium equations at different joints of the section and try to find out the unknown value of the forces that are there in the truss members. And in method of section, we cut the whole truss into two parts and then determine the unknown force required to calculate for the particular member of the truss. Then we move to the third week, wherein we have utilized the concept of unit load method based upon principle of virtual word to determine the deflection, that is, it can be the horizontal or vertical deflection of trusses at various joints. So if you are required to calculate a vertical deflection at a point, so apply a unit deflection unit load at that particular point, and then calculate the forces in all the members, utilize the principle of virtual work, and calculate the deflection value at that particular point. Okay. In week 4 and week 5, we have covered the topics related to deflection of beams and frames, where we have used the moment area method, conjugate beam method, and virtual work method to determine the deflections in the in the member at various particular points that are required to be calculated. After that, we have moved to influence line diagram. So influence line diagram is drawn for those cases wherein a moving load is transferred from one end to the other end along the length of the beam or a frame, and we need to calculate the value of reaction, shear force, bending moment at different point of the section. So influence line diagram provides us, due to the moving load, how the variation of this bending moment and shear force changes along the length of the beam. Now, this all covers the statically determinate structure. So, by this point, 50% of your syllabus for the structure analysis course is already covered. Now, we will move to the second part of this structure analysis course, that is analysis of indeterminate structures. So you might have seen, I think you have covered the videos of the seventh week, wherein we have started that to solve that this to solve the indeterminate structures. You should know that what is static and kinematic admissibility. So suppose you have a arch. So this is your say, arch subjected to uniformly distributed load over its whole length. So in this, the possible cases are that the deflection profile of the beam could be like this. Okay, and there are chances also that this profile might go like this. However, there will be only one chance at which at one point at which the structure will satisfy the boundary conditions provided at its end supports. Okay, so this is not the red and blue diagrams that are drawn, that are not the deflection profile for a two hinge beam, but it is a journal case. Suppose you have a arch, how it can deflect. It can have a deflection outwards also as well as inwards also. However, there will be only one case in which the it will follow the hinge boundary condition, in which the ends of the structure will not move, whereas the whole length of the beam will take its deflection profile based upon the loads that are acting over its whole span. So this is called as kinematic admissibility. When you apply the equilibrium equation, when equilibrium equation is satisfied, you consider the structure to be statically admissible. But when it also satisfy the end boundary conditions, then you call that structure to be statically admissible. So this is what is written. So there are infinite number of systems which satisfy equilibrium equations. That means they are statically admissible. It means they are statically admissible. But among all, there is only one system that satisfies the boundary condition. Okay, so we call this system to be kinematic admissible. So to solve such a system, we require additional conditions, because by the three conditions of equilibrium, we can't solve such kind of a structures. So we require additional set of equations which will provide us the necessary condition to solve the value of unknown components that are there in the structure. So to get that compatibility equations or additional equations to solve the structure, we have two methods. One is force method and another is displacement method. So let's get started. So to find out the value of to determine the how to use the force method, first have a brief introduction of how degree of static indeterminacy is calculated. So earlier also we have seen, so what the degree of static indeterminacy tells us that the total number of unknowns when subtracted from the number of independent equilibrium equations, it will provide us the degree of static indeterminacy. So suppose you have a continuous beam which is fits at one end, and let me erase this. Yeah, which is fixed at one end, and at some length it is supported on roller support. Yeah, like this. So in this case, what kind of degree of indeterminacy of this structure is? So in support you have three unknowns, so this will be three. So here one reaction is there, so one. So here one reaction is there, one. So your ds will be total five unknowns are there, minus three. So it has a degree of static indeterminacy to be to be two. Okay, now next thing, suppose in the same structure, in the same structure if you have hinge condition like this, so in this case, what will be the degree of static indeterminacy? So here also three reactions are there, two in the hinge support, two in the hinge support. So your ds will be 7 minus 3, 4. Okay, now what will happen when you have an internal hinge along the length of the beam? So suppose you have a continuous beam. So you have an internal hinge in between. So see, here you will be having two unknown reactions, one unknown reaction, one unknown reaction, and one unknown reaction. So if you calculate ds, your ds will be 2 1 3 1 4 1 5, 5 minus 3 plus 1. This plus 1 comes because here you will get one additional equation also, that moment about this hinge equal to 0. So you have one additional equation. So now your degree of static indeterminacy is 1. Okay, this is how you calculate the degree of static indeterminacy in case of beams. So when you have a frame structure, so then how you will calculate? So see, this is a frame. simply supported. Now you can say that this is a statically determinate structure, but also the member forces also provide unknown values at various joint of this frame structure. So to calculate the static indeterminacy, you have you can divide the degree of static indeterminacy into two. One is external indeterminacy. So in this case, you have two here, one here. So your DSE, that is degree of static external indeterminacy, will be 3 minus 3 equal to 0. Whereas your internal indeterminacy, DSI, is equal to 3 into C, where C is number of closed loops. Okay, this is how you calculate in case of frames. So now there can be such a situation when you are required to calculate in case of a continuous beam. So suppose you have a continuous beam like this. In this, you are provided with UDL along first half of the span. Okay, so how the deflection profile of this beam will look like? It will be like this. Yeah. So this will be your theta AB. Here, if you mark it, this will be your theta BA. This will be your theta BC. So in this, your delta B is equal to 0 and theta BA is equal to theta BC in magnitude terms. So that is your compatibility equation for a continuous beam at a particular point. So this is your displacement compatibility condition. Okay. So let's have a problem first for this. So suppose you are having a cantilever beam propped at free end, subjected to point load at the center of the beam P. Okay, so in this case, how you will solve this problem? So what you will do, you will first divide this whole beam into two parts like this. Okay, so now draw the bending moment diagram for first case. Yeah, so in this case, This will be your bending moment diagram. And if we convert that into, yeah, so this value will be PL upon 2EI. Okay. So now if you draw the bending moment diagram or M by EI diagram for this support condition, so it will be like this. Let this point be C and here reaction will be Cy. So this will be Cy into L, okay, upon EI. We can also write it like this. So what we have learned that the displacement of the in longitudinal beam, we have learned that the moment of the M by EI diagram will give you the deflection at that particular point. So like this, we will calculate the value of deflection. So in first case, we will find the delta C1 equal to, this will be 1 by 2 into minus PL upon 2EI into L by 2 into what is the distance from point C. So it will be 2 L by 3 L by 3 into L by, oh, sorry, 2 L by 3 into 1 by 2 because it's half the length plus L by 2. Okay. If we solve this, we will get it as minus 5 PL cube upon 48 EI. Whereas in second case, I will write it here in the bottom. So your delta C2 will be equal to 1 by 2 into minus Cy into L, or it would be plus Cy into L into L distance, acting at a distance of 2 by 3 into L. So that will be equal to Cy L cube upon 3 EI. Okay. So now your displacement compatibility equation says that your delta C will be equal to delta C1 plus delta C2. That this thing you got from the principle of superposition, but it is equal to 0. This thing will tell you the displacement compatibility at that particular point. So by this, what you will get? You will get delta C1 equal to minus PL cube upon 48 EI and plus Cy L cube upon 3 EI equal to 0. So by this, you will get to know the value of reaction at that particular point equal to 5 by 16 into P. This is how you calculate the value of reactions for indeterminate beam. So if you got the value of Cy, now using equilibrium equation, you can also calculate AY, AH, and MA using equilibrium equation. Okay, this is how we utilize the process of displacement compatibility along the different points of the section. Okay, so first see what are the various steps utilized to use the force method. So as we have used done in the previous example, in this case, what we have done, we have take divide the whole indeterminate structure into determinate as well as indeterminate structure. Okay, so we have first taken a system removing the redundant, or we can't say it is a redundant force because there is nowhere mentioned. So if we remove the prop support, this beam will be a determinate beam. So when we add a plane without loading, the second beam which is having a cantilever beam subjected to a prop support at its end. So when we superimpose this system 1 to system 2, we will get equal to the original problem that is provided to us. Okay, another thing that we can use is to change the cantilever support that is provided to us to a hinge support. So if we change it to hinge support, plus what we can add, we will also make another simply supported beam which is subjected to a unit or a moment m provided at end a along the on the beam section. Then also we will solve the problem. Then also we will get the same value of cy equal to 5 by 16p. So under what condition we have to use the moment think at point A, or what in what condition we have to remove the prop support from the point C, that depends upon problem to problem and what is our desirable purpose. Okay, so let's go to force method. So in force method, what we say that redundant forces are taken as unknowns. Okay, so these redundant forces are taken as unknowns, and additional equations are obtained by considering the displacement compatibility. Like previously, what we have done, we have got the displacement compatibility at delta c equal to 0. Okay, so what is the step involved in this? So steps are, you have to calculate the degree of static indeterminacy. So in previous case, if we calculate the degree of static indeterminacy, it comes out to be equal to 1. Okay, so then select redundant force or moment. Okay, so in previous case, what we have taken the redundant support that is provided at the end C. Okay, then you solve the solution for the determinate structure under load that we have done for system 1. Then you solve for determinate structure under redundant that we have done for system 2. Then apply compatibility equation at the release end. Okay, then solve for unknowns. So for previous example, I will write it here. So for previous example, we have ds equal to 1. So selection of redundant force, selected propped support as redundant force. Then he's telling solution of basic determinate structure under load that we have calculated by delta C1. Then solution of basic determinate structure under redundant, that is our delta C2. Okay, and use of compatibility condition at the release end. So that is delta C equal to delta C1 plus delta C2 equal to 0. So this is our compatibility equation, and what we have solved to get it. So for solving, we have got Cy first, then we have got Ay, Ah, and Ma. Okay, so this is whole procedure of solving the force method, like in the previous example that we have done. So there are another concept of flexibility coefficient also in the uh, in this force method. So what it says that, suppose you have a beam which is subjected to a uniformly axial load P. Okay, so when it is deformed, it will be compressed. So the amount of length it has moved from this position to this position is your displacement vector. It's so now your P will be equal to K into H, or you can say as K equal to P by H. So this is your stiffness, and how you define it. we define it as force per unit displacement. Okay, so how we define flexibility? So flexibility is defined as deformation per unit force. It is defined as deformation per unit force. That is F is equal to H upon P. It will be equal to 1 by K. So what we can write as flexibility is the inverse of stiffness. Okay. So for any problem, suppose you have taken, let me draw a cantilever beam. So suppose you have a cantilever beam subjected to point load at the center of the beam. This is your point A and point C. So it will deflect like this. So this deflection is represented as delta at point C due to load at point B. So let be this point is B. So this is your deflection at point C due to load at point B. So how we have defined it? We have defined it like delta CB equal to minus 5 by 48 PL cube upon EI. Okay. So if you take minus P as outside, it will be equal to 5L cube upon 48 EI. Okay. So your delta CB will be equal to minus P into FCB. So now your FCB will be equal to 5L cube upon 48 EI. So this is your flexibility coefficient. Okay. So next, if we have a beam subjected to point load at center and also it is subjected to moment at its end, then how you will solve that problem? Okay. So let it is subjected to moment M. So here the deflection profile of the simply supported beam will look like this. Okay. So this will be your complete delta A. So this is your delta theta, sorry, theta A, and here it will be delta B. Okay. So how you can break it into two parts? So you can break it like this. You have a isolated load provided at center without the moment at the end point, like this. Plus you can also add another structure which is supported to, yeah, which has a moment of M provided at the support A. Okay. So what will happen to this under the load? It will deflect like this, and your delta A delta AB. So this is your slope due to the load at point A, and this is your maximum deflection delta BB. That was theta A AB. This is delta BB. Now due to moment at about A, it will deflect like this because deflection profile can't be changed. So this is the deflection profile of the beam, and in this case, this is your theta AA, and this is your theta BA. Oh, sorry, delta BA. Okay, so your total theta A will be equal to theta AB plus theta AA in magnitude sense only. Okay, and your delta B will be equal to delta BB plus delta BA. Okay, so your theta A, how you can write it like this in theta here, it you can write it like m into alpha AA plus p into alpha AB, where alpha AA is equal to L upon 3I and FBA is equal to L square upon 16EI. Sorry, your alpha AB is equal to L square upon 16EI. Okay, and you can write the delta B also as M into FBA plus P into FBB, where your FBB is equal to L cube upon 48EI. Okay, so now writing the whole equation in matrix form, what will it will look like? It is like L upon 3EI plus L square upon 16EI, L square upon 16EI plus, sorry, fourth value will be L cube upon 48EI. Join in with the value will be M and P. So what you will get here? You will get here as first is theta A, and this will be your delta B. Okay, so this matrix that you have developed, this is your flexibility matrix. Okay, so next equation, what it tells like, if you reverse this matrix, or if you invert the matrix and take it to this side, so your value will be equal to 7, sorry, your value will be 48 EI upon 7 E cube L cube equal to L square minus 3L 16 into M into theta A plus delta B. It will be equal to M into P, M and P. Okay, so this we have got from the Maxwell-Betty law. Maxwell-Betty law of reciprocal deformations. So this is your stiffness matrix. Okay. So if you have uh, determined the flexibility matrix, if you invert the matrix, you will get the stiffness matrix. So this is also called as the building block of displacement method, stiffness matrix. Okay. This is how you will solve the problem of stiffness matrix as well as the force matrix. So in stiffness matrix, you are required to calculate degree of freedom. So what are the degree of freedom? So in degrees of freedom, the main definition what it says that the degree of system of a mechanical degree of freedom of a mechanical system is the number of independent coordinates required to completely specify the configuration of a system. So it means that suppose you have a roller support. Okay. So in that, you have only one degree of freedom. In case of hinge support, you have on you ha- you sorry. In case of roller support, in vertical direction as well as in rotation, the support is free to move. So that is your degree of freedom is 2. Whereas in case of hinge support, only rotation is free, whereas the vertical and the horizontal displacement are restricted to move. So in that case, your degree of freedom is 1. Whereas in fixed support, neither the displacement is allowed nor the rotation is allowed. So in that case, your degree of freedom is 0. So that is what you will see in kinematic indeterminacy. So this is what we are saying in kinematic indeterminacy. So kinematic indeterminacy tells you that in a skeletal structure, what are the total number of degree of freedom at various joints. Okay. So suppose you have a truss frame. Yeah. This is your simply supported truss frame. Okay. Pin jointed at each and every end. So in this case, you have, so it is hinge. So it is like this: two, 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 and one. Yeah. So in this case, your decay comes out to be 9. So if you solve for ds also, so what you will get ds. So ds here is how you will calculate m plus r minus 2j. It will be equal to where and 1 2 3 4 5 6 7 8 9 9 and r is 3 minus 2 into 6. So it will comes out to be 0. Okay, so this is how you will calculate dynamic indeterminacy and static indeterminacy of various structures. Okay, so now let's solve few problems related to that what we have covered. So finally, what let me first summarize the difference between the force and the flexibility matrix. Not matrix, it's method. So in what steps we have followed in force method, what steps we have followed in displacement method. So we will see that. Okay. So in force method, we will find the degree of static indeterminacy. Okay. So here the main purpose is degree of static indeterminacy. Whereas in case of displacement method, we will find the degree of kinematic indeterminacy. In force method, we take the force to be redundant, whereas in displacement or stiffness method, we identify unknown displacement in the structure. Okay. uh, Stiffness method in detail we will see in the next week also. So in force method, we will find the displacement in the basic statically determinate structure under load and redundant forces. That is what we have done, that we have taken break the whole structure into determinate and the redundant uh, structure, and then determine the value of deflection at different points. Okay, so here we will determinate and undeterminate under redundant forces, whereas in case of stiffness method, we will restrain the above displacement and find the forces in the basic kinematic determinate structures. So after finding the unknown displacement, we will restrain that particular point and try to find out, due to restrainment of displacement at that particular point, what kind of forces are developed at different points of the beam. Okay, this is how we utilize the displacement method. Okay, here the displacement are expressed in terms of the redundant using flexibility format. Here forces are expressed in terms of displacement using stiffness format. Okay, here we will solve the compatibility equations and find unknown reactions or redundants. Here we will solve the equilibrium equations to find the unknown displacement. This is the major difference between the force and the force and the displacement method that we have solved. So currently what I have shown you is the force method. In how to utilize the displacement method in detail, we will see in the next week. Okay. So let's solve some problems related to that. So in this case, you are required to calculate the degree of static indeterminacy for a plane frame. So in plane frame, you will see that here you are required to calculate the number of unknowns that are there. So see this. Here you are having three unknown reactions. I will choose different color because diagram is also blue. I will choose black. Okay. So here you are also having three unknowns and reaction. Okay. In this point also it is fixed. So you will be having three unknowns. This, this, and this. Here also you will be having only one reaction because of roller support. Okay. This thing. Now in this whole frame, if you cut the section, you will get, you will be having one shear force and one moment at the different points. So you will get one force and one moment this side, and here also you will get one force and one moment. Okay, same thing is developed in other members also, like this is the force you will develop, and these are the reactions that are developed. So these are the forces, these are the moments that are developed, these are the forces, and these are the moments that are developed in the frame structure. So if you count the number of unknowns, so in this point there are four, 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 here three, and one. So your total R is 19. Okay, minus and is here is 3. So your degree of static indeterminacy will become 19 minus 3 into 3. And then your ds will be 10. Okay, so this is how you will calculate the degree of static indeterminacy for a plane frame like this. If I move to next question, this is a simple question. So here you are required to calculate the degree of kinematic indeterminacy. So in kinematic indeterminacy, you are required to find out the degree of freedom at a particular joint. So here the degree of freedom is 0. Here also degree of freedom is 0. Whereas this joint can move like this also. It can move like this also. Okay. And moment will also be developed. Okay. So 1, 2, 3. So your dk in this case will be 3. Okay. So this is how you will solve the problems for degree of static indeterminacy and kinematic indeterminacy. Now again you have to determine the kinematic indeterminacy of the following beam provided the structure which is axially inextensible. Okay. So now it is also mentioned that is axially inextensible. So what will happen here? You will be having 0. I will take different color. 0 degrees of freedom. So kindly remember that kinematic indeterminacy is related to degrees of freedom, whereas the static indeterminacy is related to number of unknowns that are there minus the number of equilibrium equations that are in the structure. So at A, degree of freedom is 0. At B, since we have degree of degree of freedom for a roller support equal to 2, but here it is also mentioned that the member is actually inextensible. It means you have another degree of freedom uh, to be restricted that is along the x direction. So here you will be having 2 minus 1 equal to 1. Okay. In hinge also your degree of indeterminacy will be 1. Okay. Whereas now coming for the internal hinge. Internal hinge can have moments. This kind of moment also is there. This kind of moment is also there. And also reaction force is also there. Okay. So 3 here also. So your total dk will come out to be, so your dk is equal to 0 plus 1 plus 3 plus 1 equal to 5. Okay. Yeah. So in this case, you have to find the static indeterminacy of a truss. So what is the formula for truss? So ds is m plus r minus 2j. So it's like number of unknowns it minus the total number of equilibrium equations that will also give you the same thing. So this is your unknowns minus this is equilibrium equations per joint. Sorry, equilibrium equations per joint. So in truss only you have summation of horizontal force equal to 0 and summation of vertical force equal to 0 because there is no moment in the structure. So that's why 2 into J. Okay. So in this case, you have members 1, 2, and 3. M here is 3. R here is 4. 2 into 4. J is 1, 2, 3. 3. If we solve the problem, we will get ds equal to m is 3 plus 4 minus 2 into 3, 6. 7 minus 6, ds will be equal to 1. Okay? Yeah. This is how we will calculate the static indeterminacy of a truss. Now let's move to calculate the static indeterminacy of a truss, like in this case. So again, your ds will be equal to m plus r minus 2j. Now here your m will be, I will mark it like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13 into 13, 26, and plus 1, this one, it will be 27. Okay, so let's write about r. R here is, this is 2, this is 1, so your r is 3. Now let's write j. So your j is 1, 2, 3, 4, 5, 6, 7, and 1, 8. So here 7 into 7 into 7 into 2, 14, and 1, 15. So your j will be 15. So your total ds will come out to be 27 plus 3 minus 2 into 15. 30 minus 30 equal to 0. So your ds in this case is 0. So this is your statically determinate structure. In next question, you also need to find the degree of static indeterminacy of the beam given below. In this case, your static indeterminacy, so your unknowns here are 2 in hinge support. In roller support, it is 1. In roller, it is 1. 1. In fixed support, you have 3. So your ds will be 2, 1, 3, 4, 5, 1, 3, 8. 8 minus number of equilibrium equation will be 3 equal to 5. So your ds in this case will be 5. Yeah. Now, how many redundancies are required to be removed to make the beam to be statically indeterminate? So, to make the beam to be statically indeterminate, you are required to determine a degree of static indeterminacy. So, to make the beam as statically determinate, it is required to calculate degree of static indeterminacy. So in this case, your ds will be equal to 3 plus 1, 4 minus number of equilibrium equations equal to 3. So your ds will come out to be 1. So if you remove one redundancy, whether based upon the prop support or based upon the moment release from the fixed end, both are both are cases to make this prop cantilever equal to the determinate structure. Okay. So in next question, you are required to calculate the degree of kinematic indeterminacy. Okay. So in this case, The kinematic indeterminacy is this. Here it is 1. Here it can move in horizontal direction also. 1. And rotate also like this. This. Here it is 0. Fits with support. And at each and every joint, it can rotate and also translate. So since it is a rigid joint, not a pin joint, so the whole frame will move like this. Whole story will move like this, this, because it is a rigid joint, not a pin joint. Okay. So you have 5 deformations at each and every floor, and moment at each and every point. I think I should change the color. Okay. So your total decay will be equal to, in each floor it is 4, 4, 8, 12, 16, 20, 20 plus 5 horizontal deformation at each floor. Okay. Plus 1 in hinge support, plus 2 in roller support. So your decay will comes out to be 28. Okay. This is how you solve the problem of kinematic indeterminacy of of the frame which is provided to you in this current torsion. Now, in this torsion, you have to utilize the concept of force method to determine the value of the reaction at a particular point C. Okay, so let's read the question first. So, in the following statically indeterminate beam, consider the vertical deflection at point C as redundant force. Okay, so here it is telling that this is our redundant force. Okay, now we are expected to calculate the vertical displacement at point C, okay, which is described by D1 for the beam with point load. Okay, so we have to find in system 1, D1 at C. Next is you have to calculate the vertical displacement at point C D2 for the redundant force dy. So in system 2, you have to find D2 at C. Okay. So and consider the flexural rigidity of the beam as EI. Okay. Got it. So let's draw system 1 first. So your system 1 will be like this. So your cantilever beam with no prop support and point load provided at the mid of the section. This is your 10. This is 5. This is 5. Okay. So now made the bending moment diagram for this. It would be like this. So this will be the maximum value will be 10 into 550 upon EI, and this length is 5. Okay, so let's mark the point A, B, C. This is also A, B, C. So your D1 will be equal to 1 by 2 into what is the length? 5. Maximum displacement 50 upon EI, and it will be, we have required to calculate at point C. So it will be 5 plus 2 by 3 of 5. Okay, so your D1 will be equal to 250 upon 2EI multiply by, so this will be 3 into 3 plus 2, 5, 5 by 3, 25 by 3, and your D1 will be equal to 3125 divided by 3EI. So D1 you have calculated. Now in system 2, you are provided with a cantilever beam with prop support at its end. So in this case, if it become free, yeah, okay. So this value will be, the whole length is 10, and let this reaction will be equal to Cy. So your maximum value will be 10 into Cy, and this length is also 10. Therefore, your D2 will be equal to 1 by 2 into 10 into 10 Cy into 2 by 3 of 10. Okay, so your value will come out to be 1000 Cy upon 3 EI. Okay, we also write it as 10 upon EI, and this is 51 EI, 3 EI. We can also use direct formula, as here you have the formula as D2 will be equal to maximum PL cube upon 3 EI. Okay, now you have calculated D1 and D2 in both the cases. Okay, this is what it is required in the question. Now, in the same question, you are expected to use the compatibility equation at the joint C and calculate the value of reaction support at point C. So what will be the compatibility equation at point C? So using principle of superposition and displacement compatibility, delta C will be equal to D1 plus D2 equal to 0. This implies, what is your D1? D1 is 3125 upon 3EI plus, what is your D2? D2 is 1000 CY upon 3EI equal to 0. So this will give you 1000 Cy equal to minus 31 minus 3125. This will give you Cy equal to minus 3.125. Let me write as unit. Okay. This is how you will calculate the value of reaction using principle of superposition and displacement compatibility at different points. So by this, I have covered the whole problems that are related to what you have covered in week 7 of the structure analysis course. So in this week, what we have covered, we have covered the introduction to both force method as well as in stiffness method. In force method, you are required to calculate the degree of static indeterminacy. So we have solved various problems pertaining to calculation of degree of static indeterminacy of the frames as well as for the beams or and continuous beams. Whereas in stiffness method, you are required to calculate the kinematic indeterminacy of the structure. So kinematic indeterminacy of the structure is related to the degree of freedom. So degree of freedom, if you will calculate, you will be getting the value of kinematic indeterminacy of the structure. So we have also solved few problems related to determining of kinematic indeterminacy of the structure. Then we have also applied the principle of superposition and displacement compatibility to determine the value of unknown reaction in statically indeterminate beam to find out the value of reaction at particular support point. So if we have got one that support point reaction, other reaction can be calculated very easily. So this is what we have covered in this week. So if anyone has any question, they can directly ask right now, or they can also post their queries in structure in discussion forum provided to you in Swayam app, wherein the team members will try to resolve your queries as early as possible as you post in the discussion forum. So by this week we have covered, where is the slide? So by this week we have covered the introduction to uh, force as well as the stiffness method. In the coming week, we will see how to use the method of consistent deformation to determine for the plane truss that how the deflection and slope is varying along the members. Okay, so first part of the structure analysis course is over. That is analysis of statically determinate structure. Now we are moving to statically indeterminate structure. You have to spend some time to determine to get it familiar with the force as well as the stiffness method and the indeterminate structure, how you will solve the problem related to that. And in this current week we have solved, let me go there. So in this current week, yeah, in this current week, we started with definition of statically admissible and kinematic admissible for a particular structure. Then we have moved to determine the degree of static indeterminacy, and then how we can utilize this concept in frames also, and how we can define the displacement compatibility of a continuous beam or any indeterminate structure and we have calculated the value of reactions based upon the displacement compatibility that is provided to us. And then we have moved to force method, that how force method is utilized in this whole process. And we have also defined the flexibility coefficient as well as the stiffness coefficient for the member. And finally, the degree of freedoms, what it says and how it is required to be calculated, we have covered. And we have finally distinguished between the force as well as the displacement method. Problems related to that are many. Few of them are covered so that you will have a overall glimpse to the picture that how you can determine the degree of static as well as the kinematic indeterminacy, and also in indeterminate structure how you will calculate the value of unknown reaction using principle of superposition and the what is that what was that displacement displacement compatibility equation. Okay, so by this I am ending this session. Hope you have gone through each and every slide in detail, and if you have any question you may ask us. We will be having 3 sessions every week. First will be on Saturday, second is today on Sunday, and another session will be on Tuesday. All of us TAs are currently working hard to solve your queries as easy as possible. So by this, I will end my session. Hope you have liked this session. Enjoy your weekend. Have a nice day.